equations and inequalities have some similarities and they have some differences. They're like equations in that we use the same steps to solve them, but an equation is a statement of equality. So if you have your balance scale, the two sides are going to be at the same exact level. An inequality is a statement that says one quantity is greater than another. Or less than another. It depends on how you want to look at it. Okay. When we solve inequalities, we use the exact same steps as solving equations, except with one small difference. And that difference comes if we have to multiply or divide by an excuse me. So inequalities also have multiple solutions. Actually, infinite solutions. So like if I say x is greater than 3, x can be 3.1, 5, 276, 50 million, right? It's any number that's bigger than 3 throughout all the numbers, which means you have an infinite number of numbers. So with an equation, we're going to have one, none, or infinite solutions. With an inequality, we're either going to have an infinite solutions or no solutions. Okay. And in order to represent them graphically, we graph them on a number line. So this is set builder notation. We talked about this in chapter 2. Remember that this line means such that. So the sentence for here would be x such that x is less than a. Okay, so if I had this graph and I said this number right here is a, less than gives me an open circle, and I'm going to shade the side where all the numbers will be smaller than a. Okay. X such that x is equal to a. So again, if a is right here, that's the only value it has, so it's just got a single dot. X, I'm just going to put st for such that. X is greater than b. So if b is right here, I make an open circle for greater than and shade everything larger than that. I don't know why I put an equal to here. We already did that, so just ignore that one. Okay, x such that x is greater than a and less than b. So it's between the two, which it looks between the two here. So we have an a, we have a b, we have open circles, and we shade in between them. Oh, so this symbol right here should be like that, and this symbol right here should be like that, and this one should be like that. Oops, like that, and this should be like that, and that should be like that, which makes this, oops, too big of an eraser, completely different. Less than, less than, less than. This is less than or equal to. Okay, so this symbol. The difference between a less than and a less than or equal to. Open circle, closed circle. Do you guys remember that? Okay. Sorry about that. And then this is greater than or equal to, so with a B, closed circle, and everything greater. Okay, if we have two less thans, you have two open circles. If we have two less than or equal to's, you're going to have two closed circles. Okay. If I have a less than or equal to and then a less than, the equal to is next to the A, so that one gets the closed circle, and then the regular less than is next to the B, so that one gets the open circle. You shade between them. And then if it's the other way around, the less than is with the A gets the open circle, and the less than or equal to is with the B, so that one gets the closed circle. Less than or greater than gives you an open circle. Less than or equal to, greater than or equal to gives you a colored in circle. And the reason being is because the equal to means that it also includes that number where you're putting the circle, whereas the just less than or greater than does not actually include that number. So if I say x is greater than 3, x can't be 3. It can be like 3.000000001. So almost 3, but it can't actually be 3. And that's what that circle indicates, that it can't actually be 3, whereas if it's less than or equal to 3, or greater than or equal to 3, it can actually be 3. Yeah.
When you're dealing with two of those,
yeah.
Is it always in between?
It's always going to be in between if it's written like this. So if we have, like say 2 less than x less than 5, do you see how x is actually between the 2 and the 5 in the sentence? So x will always be between them. Now if I had x is less than 2 and, or x is greater than 5, then it's not going to be between. Because you can see that this side is less than 2 is going to shade over here on this side of 2, and greater than 5 will shade over there on that side. But if it's written as a compound inequality like this combined, it's going to shade in between. Does that make sense? Okay, graphing the sets. Now, some people are very particular about graphing on number lines and want you to draw a nice straight, hold on, I can't draw a nice straight line. Get a ruler and draw a nice straight line. And then start putting numbers on there. About the same distance apart. And then graph. X is less than 3, so I'm going to have an open circle on 3. And everything less than is over here. So I'm going to shade all of this. I am not that particular. I require your number line to have 2 numbers on it. 0 and then the number of reference. So you can draw a line, put a 0 on it. My next number is a -1. Make sure it's on the correct side of 0. Don't be putting -1 way over here. Okay, that's why the 0 is there. The 0 is your reference point to your new number. I have a greater than or equal to, so that gives me a solid, and we're shading this way. As long as you have those 2 numbers on there, they're golden. Here I have x such that -1 is less than x, which is less than or equal to 3. So in this case, I'm going to have those 3 numbers. Open circle because of the less than, closed circle colored in because of the less than or equal to, and then X is between them, so I shade between. Like I said, we're going to use the same exact steps as solving equations. So step 1 would be to distribute if possible, or if necessary. Step 2 is going to be to collect like terms if necessary. Then add or subtract, and then multiply or divide. And I'm putting a little star right here because the multiplying and dividing step has an extra step if we use a negative. So no distribution, no collecting like terms, so I'm just going to add 7 to both sides, which will give me 4x is greater than or equal to 12. I'm dividing by 4. So x is going to be greater than or equal to 3. It says to solve. Okay, I don't know how that happened. It said to solve and graph. Greater than or equal gives me a solid. So we've got our circle for has the equal that's colored in, and then greater than is on this side. Okay. 1/3 x is the same thing as saying x divided by 3. But to get rid of one of these fractions, a half, a third, a fourth, a fifth, multiply by the denominator. And what that does is those will cancel out. You have to do both sides so to make it legitimate. Okay, so I have x less than or equal to 15. Okay, this is why it's nice that I'm not really picky about the number lines. Otherwise you'd have to make me a 15 lines. Less than or equal to, we're going to color in a dark circle from the equal to and shade this way. We're negative. I'm just going to rewrite it so I can actually reach it well. Okay, now whenever we multiply or divide by negative with an inequality, yeah. We're to flip the inequality. Okay, so I'm going to divide both sides by -3, which is going to give me an x and a -7. Then I have to flip that over and make it a less than. Okay. The reasoning being is because whenever you multiply or divide by negative, you're switching sides of the number line. So you have to switch sides of the inequality. Graphing, I have a 0, I have a -7, open circle because we're a less than. And then everything over here gets shaded. That's a 7, not a 1. Okay, here I have variables on both sides, and I've been moving variables always to the left, but that's just because that's where I like them. You can go either way. I'm actually going to leave them on the right this time because I want to make sure that people are not falling into the trap of shade where the arrow points. Okay, so I'm going to subtract 6x from both sides. And I'm going to get negative 12 is greater than or equal to 2x plus 2. I'm going to subtract 2, and I get negative 14 is greater than or equal to 2x. And then I divide by 2, and I get negative 7 is greater than or equal to x. Now, up until this point, we've been shading the same side as the arrow points, and I think some people teach it that way. Shade where the arrow is pointing. That only works if the variable is on the left. When the variable is on the right, if I were to shade this direction, I would be lying, because what I'm saying is x is less than negative 7 here. So if I shade the way the arrow is pointing, I'm shading greater than negative 7. So be aware. Yeah, so it's the opposite. So be aware if your variable is on the wrong side. It's not that it's the wrong side. It doesn't matter which side the variable's on. But for shading purposes, we're just going to call it the wrong side. If your variable's on the left, cool, shade the same direction as the arrow. But if your variable's on the wrong side, shade the other way. Okay, so just be aware. So this time we're going to have a closed circle because it's got a less than in there. And it's this way. And if you think about it, just to double check yourself, like this is saying that negative 7 is bigger than x. Think about like where that would be on the number line. Negative 7, if x is smaller than negative 7, it has to be on this side. You know, just as a way to double check to make sure you're shading the right direction. You think about where would x have to live if it was smaller or larger than whatever number you're talking about. I'm going to distribute first. So I'm going to distribute this to, I'm going to draw these upside down because I don't have any room on top. And I'm going to distribute that 8. Okay, 2x minus 6 plus 5x is less than 8x minus 8. So far with me? Okay, then I'm going to collect like terms. 2x and 5x is 7x minus 6 is less than 8x minus 8. I'll go back to the left. Negative x minus 6 is less than negative 8. Add 6. Negative x is less than negative 2. Now with equal signs, whenever you got a negative x, I just said change both signs. Which you can still do, you just change both signs, but if I change this sign, I have to flip my inequality. So negative x is less than negative 2 means x is greater than 2. Okay, so if you change signs, you have to also flip. And the reason you have to flip it is because when you change signs, technically, you're either multiplying or dividing by negative 1. However you want to look at it. But that's how you change a sign, is to multiply or divide by negative 1. So you multiplied or divided by negative, which means you have to flip the sign. Okay. Any questions so far on inequalities with just one inequality symbol?
How did the negative become a positive?
Here, because the x is also negative, and we don't want to know what negative x is. We want to know what x is, so I changed the sign on the x, so I also had to change the sign on the 2. Any other questions? That was a good question. Okay, 3-parters. Part 1, part 2, part 3 zones. You can either solve these all in one, or you can split them and solve them as 2 separate problems. Okay, so I'm going to do an all in one, and I'm going to do a 2 separate. You will get the same answer no matter how you do this, but for some people, one way is easier than the other way. So I want to show both. We talked about equalities, equations, and inequalities, and I always say do the same thing to both sides, do the same thing to both sides, do the same thing to both sides. On this one, you're going to do the same thing to three sides. The right, the left, and the middle. Okay, so I'm going to subtract 1 from here. Means I also subtract 1 from here and from here. So negative 4 is less than 2x is less than or equal to positive 4. And then if I divide by 2, I have to divide by 2 here and here. So I get negative 2 is less than x is less than or equal to positive 2. Okay. If that's confusing, you can split it into 2 separate problems. So let me actually move that. Higher. So I have negative 3 is less than 2x plus 1 is less than or equal to 5, right? Well, if we look at this, that's one problem. Negative 3 is less than 2x plus 1. And here's another problem. 2x plus 1 is less than or equal to 5. So if you don't like solving it all together like this, you can split it into those 2 separate problems and solve each one individually. Okay. Subtract 1 from both sides. Divide by 2. You get negative 2 is less than x. And then come over here and you subtract 1 from both sides. Divide by 2. We end up with the same answer. It's just separate. And that's okay. You just have 2 answers over here. So it's a matter of preference, as far as I'm concerned, which way you go. You can do it all in one, or you can split it into 2 problems and solve it that way. So average. Okay, add all the numbers, and then divide by how many you added. The one where you're talking about we take the highest and the lowest and then we add them, divide by 2, you're looking for the median there. Okay, so we're going to add up all the numbers and divide by how many you added. The other thing that you need to know to be able to work this problem is what this term right here means, at least. You want an average of at least 90%. Okay, if you say at least, that means that's the very minimum that you'll accept, right, or that you want. So you want that or more than that, so greater than or equal to. So at least means greater than or equal to. On the opposite, at most means less than. So if, like I said, I have at most $5, that means I have $5 or I have less than $5, right? So at least is greater than or equal to, at most is less than or equal to. The symbols are actually opposite from what the words sound like they would mean. Okay, so we want at least 90%, so we want greater than or equal to 90%. You have 5 tests. On the first 4, you have 86, 88, 92, and 84. Then the final exam counts as 2 grades, so it counts twice. what do we need to get on the final to earn an A in that particular course? Okay, so what I have an 86, an 88, a 92, and an 84, and the last test counts twice. So I'm going 1, 2, 3, 4, 5, 6 numbers that are getting added together. So I have to divide by 6. That's why I kept the x's separate instead of saying 2x, because you need to count it as 2 separate tests when you're doing your average. And we want that to be greater than or equal to 90. Okay. Now that I've got that set up, I can add those together and get 2x, and I can add all these together and get some number. Ready? So I'm going to add 86, 88, 92, and 84. So that's 350. And then 2 x's divided by 6 needs to be greater than or equal to 90. Multiply both sides by 6. Those will cancel. So 350 plus 2x needs to be greater than or equal to 540. Subtract 350 from both sides. So 2x needs to be greater than or equal to, I think, 190. Yeah, 190. Divide by 2. You have to get at least 95 on that test to get an A in the class, for that particular class. A binomial is a polynomial with exactly 2 terms. The prefix bi means 2, bicycle, 2 wheels, bifocal, 2 focuses in your glasses. When we multiply binomials, we can use the FOIL method or the table method. FOIL stands for first, outside, inside, and last. Okay. The table is like a multiplication table. It's just like that one on the back there where you have 12 and 12, and you can look, see what they multiply to equal. Okay. So multiplying this using FOIL method. We multiply the first. X times x gives me x squared. We multiply the outside. X times 4 gives me 4x. And multiply the inside. X times 3 gives me 3x. And then I multiply the last. X times 3 times 4 is 12. And then I collect my like terms there in the middle. Taylor method gives you the same answer. It works very similarly, but instead of drawing lines for what you're multiplying or whatever, we make a table. Okay, and you make as many rows and columns as you have terms. So I'm doing binomials, so I have a 2 by 2. So x plus 3, x plus 4. X times x gives me x squared. X times 3 gives me 3x. 4 times x gives me 4x. 4 times 3 gives me 12. The nice thing about table, this is your first term, this is your last term, and your like terms line up on diagonals. So no matter how big the polynomials you are multiplying, you can be doing a 5 by 5. Your first and last term will be the top and bottom corners. And then if you draw lines at the diagonals, those will all be your like terms. The like terms always line up on diagonals. So that's what you add together. 7x squared. 4 plus 3 is 7. Plus 1. Same answer, different format. Okay, so FOIL first, outside, inside last. 3x times 5x is 15x squared. 3x times negative 3 is negative 9x. 5 times x times 4 is 20x. And 4 times negative 3 is negative 12. 15x plus 11, 15x squared, plus 11x minus 4. Table method, 3x plus 4, 5x minus 3. Like terms. Same answer. Okay. Whenever we multiply two binomials, we get a trinomial. And that is if we have a single variable. If you have more than one variable, if you have two binomials and like one say has x and y and the other one has 3 and x or something, you'll get a 4-term polynomial instead of a 3-term. But if you only have one variable, you get a 3-term. Okay. This is known as a quadratic expression. Any single variable expression where 2 is the highest exponent is a quadratic. Now, if I took the 15x squared off, it's not a quadratic anymore. It has to have the 2, and 2 has to be the highest exponent. But if I took the 11x out, it's still a quadratic. And if I take the 11x and the 12 out, and it's just 15x squared just sitting there by itself, it's still quadratic. It's just considering that that's a 0x and a 0 plus 0 on the end. Okay? So quadratics are single variable expressions with the exponent of 2. The highest exponent being 2, and they have to have an exponent of 2. Here's why I prefer table to FOIL for anything that's not binomials. Okay, ready? If you're doing a modified FOIL, it's actually you're using the distributive property. I have to multiply every term in here by every term in there, and if I'm going to keep track of it, I'm going to draw lines. So I'm going to do this one times this one times this one, okay? And then I'm going to come in here and I'm going to do this one times this one times that one. And then this one times that one and that one and that one. And then this one times this one and that one and that one. Can you see how it might be very easy to miss something doing that? It can be very easy. So when I have a big polynomial, I think the table is nice because you can't miss anything. I've got 1, 2, 3, 4 by 3. Okay. 2x squared times 3x to the third is 6x to the fifth, 4x to the fourth, negative 10x to the third, 6x squared. And I come and do my 4x's. 4x times negative 3x to the fourth, negative 8x to the third, 20x squared, negative 12x, and then negative 10. You can't miss anything, because if you miss anything, you're going to have an empty box. Then you don't have to worry too much about trying to find all the like terms. They line up for you nicely on the diagonals. These will be together, those three, these 2. And then this is the first and last term. So when I put this together, I have 6x to the fifth, negative 12 plus 4 is negative 8. Negative 30 minus 8 is negative 38. Minus 10 is negative 48. Negative 20 plus 20 is 0. Plus 6. Negative, or 50 minus 12 is 38. And then minus 30. It's compact, it's organized, and you run less risk of forgetting to multiply something. So that's kind of why I show the table. Not really for the binomials, because with the binomials it's not, whatever, it doesn't really matter that much. But when you get into multiplying larger polynomials, the table is really nice to help keep track. When we factor trinomial, we're trying to factor it into 2 binomials. Because if we multiply 2 binomials, they give us a trinomial. So we're going to look at the trinomial and see if we can turn it into 2 binomials. Okay. There's the factor sum table. And then there's big giant X. Factor sum table is kind of the traditional way people look at it. You make a table. You take this last term here, the 12, and you look for factors of 12. And you want them to add up to the middle term. You want them to have a sum of 7. Well, probably, most likely, that pops into your head pretty quickly because they're in small numbers. But if it was like factors of 48 with a sum of 19, let's say, you might not come up with it really quickly. So we start, you go through and you list factors of 12, 1 and 12, 2 and 6, 3 and 4. And then you add them together. And then you go, ooh, that one works. And then these become what goes in your binomial. Okay. So those go here and here. Now, my favorite way to do this is what I call big giant X. So first we make a big giant X. Okay. And then I put a plus and a multiplication. And then it's a puzzle. I'm looking for 2 numbers to go here and here on the sides of the X. That when I add them, I get 7, and when I multiply them, I get 12. So you start thinking of things that multiply to make 12, and then you add them up and they make 7, and you get 3 and 4. And then those are the things that go here. Coefficients on the x's. and that makes it, or on the x squareds, it makes it a little easier. Factor sum table or big giant X?
They do both.
Sure. Okay, I'm going to do factors of 8 that are going to have a sum of 6. Well, the factors of 8 are 1 and 8 and 2 and 4. That's really all we've got. 2 and 4 add up to 6. With big giant X, I would be looking for numbers that added to 6 and multiplied to make 8. And I say, okay, 2 and 4 make 8 and add up to 6, and either way, I'm going to get x plus 2 times x plus 4. Now you can always check yourself on these by foiling it back out, and if it foils out, it should match what you started with. Here I have a negative. So I'm going to start with big giant X. I want to add up to 2, but I want to multiply to make negative 35. Be sure to keep those signs. So when this is negative and this is positive, I'm looking for a difference actually. I'm looking for two numbers that have a difference of 2. Because a negative and a positive multiply to make a negative number. Okay, so the numbers that multiply to make 35 and have a difference of 2 are 7 and 5. And then I decide, well, which one's negative? If the sum up here is positive, I want the larger number to be positive. If this was a negative 2, then I would want the larger number to be negative. But since this is positive, that makes this negative. Make sense? So I'm going to have x plus 7, x minus 5. Okay, so your larger number, whichever of these two is larger, will match this sign. Good? Alrighty. If you have a leading coefficient, that's this front coefficient on the x squared that's not 1, it gets a little bit more complicated. I'm going to show you the easiest way, in my head anyway, and then if it's confusing, I can show you other methods. But the way I'm going to do it first is the way I think is the easiest. Okay. I take the first term and the last, and I multiply them together. Okay. So I need 3 times 28 is 84. Now, I'm going to look for two numbers that when I multiply them, they're going to give me 84, but when I add them, they're going to give me a negative 20. Okay. So I start thinking of factors of 84. Well, 2 and 42, that's not 20. 7 and 12, not 20. Close, but not quite. Two things that will multiply to make 84, but add up to make 20. Sometimes it can be challenging, right? So here's a trick. We'll come over here and we'll make a factor tree. Those are all of my factors. 2 2s, a 3, and a 7. If I do 2 times 2 times 3, that's 12 times 7. That adds up to 19. If I do 2 times 7 is 14, and 2 times 3 is 6. 14 and 6 add up to 20. So that's a way to do that. You just do different combinations of the factors, just kind of, or you can make like a factor table and start just listing factors and seeing what will add up. 6 and 14. This number is positive, but this one's negative. That means both of these are negative. Because two negatives multiply to make a positive, but add to make a negative. Okay. Now, these don't go inside the parentheses yet, because I have to figure out how to split this 3. What these do is these replace that. And instead of having 3x squared minus 20x, I have 3x squared minus 6x minus 14x. And, well, I'm going to in just a sec. I'm going to factor by grouping. Do you see how these two have something in common? And then these two have 14 in common? That's what I did. I found the thing that they have in common, basically. I split it to make it easier to factor. I'll show you guys another method. To me, this one's the easier one, but that doesn't necessarily mean it's the easier one to you guys. So, I split this in half. Both of these have a 3 in common and an x in common. X minus 2. 14 times 2 is 28, so I want to make that much, so I'm going to take out the negative 14. And that gives me a positive x and a negative 2. And then those match. And then we have that. The other method that they teach, we do factors of 5, factors of 8, and we want a sum of negative 14. And we have to do combinations. Factors of 5 is only going to give me 1 and 5. If I use 1 and 8, I have 1 times 1 and 5 times 8. You have to kind of do that, FOIL them, sort of. So if I did that, it's going to add up to 41. Or I can do 1 times 8 and 1 times 5. And 8 plus 5 is 13. So it's still not what I want. Okay, so then I try different factors of 8. I could try 2 and 4. So 1 times 2 is 2, 5 times 4 is 9, 20. Oh, 20. 5 times 4 is 20, 1 times 2 is, so that's 22. And then I can try 1 times 4, and 5 times 2, that's 10, and 4, so that's 14. So far, I found them. I needed to multiply my 1 times my 2, 4, and my 5 times my 2. Okay. So I'm going to have an x, and I'm going to have a 5x. The 5 needs to multiply by the 2. That means the 2 has to go here. The 1 is going to multiply times the 4, so that goes here. They're going to add up to a negative number and multiply to be a positive number. That's a full number. Sorry. So that's the other method I know. Common things to look for. Positive, positive. These are both positive. Your factors will both be positives. negative positive, and factors are both negative. If C, the last number is negative, and the middle number is positive, one factor is positive, one factor is negative, and the positive one is greater. And then if the last term is negative and the middle term is negative, you have one positive, one negative, and then the negative one is greater. Well, negative is never greater than positive. Bigger. I should say bigger. Change that up, make that bigger. Because positive is always greater. Okay, so that's just some hints when you first look at it to know what you're looking for. Here you're looking for two positive factors. Here you're looking for two negative factors. Here you're looking for one of each with a positive one that's a bigger number. And here you're looking for one of each with a negative one that's a bigger number.